Okay, this is our Chapter 15 video for Physics 1. This is our last chapter, so this will be our last series of videos. And in this chapter, we're talking about thermodynamics. So thermodynamics is the motion of heat energy. And so we're going to start with the first law of thermodynamics. And that is that the change in internal energy of a closed system is equal to the energy added to the system minus the work done by the system on its surroundings. So we have some variables here. We have delta U. Now we used U in the previous chapter to denote energy, total energy of a system. So the change in energy, the change in the total amount of internal energy is equal to Q. Now we used Q before to denote heat flow. So the heat goes in and work goes out. So one example of this is a steam engine. There goes our little Thomas the Tank Engine there. So a steam engine is an example of an engine in which you put heat into it by burning coal and you get work out of it. And so that is going to change the overall amount of internal energy. So you do have to be kind of careful about the language here, whether we're talking about things going into or out of a system. So if we look at this first example, 15.1, this is a little bit of a trick question here, because it says if 2,500 joules of heat is added into a system. So we've got 2,500 joules of heat going in to this system, and 1,800 joules of work done on the system. Notice it's on the system, not by the system. The system isn't doing work on something else. The work is also going into the system. So in this case, we're not using heat to do work. We're putting heat into the system and we're putting work into the system. So the total change in energy is not heat minus work. In this particular case, it's heat plus the work. The delta U is going to equal 2,500 joules. And then we can either think of this as plus 1,800 or minus a negative 1,800. Because, like I said, the wording here of this problem says that the work is done on the system. So we're putting work into it rather than using the system to do work on something else. And so that gives us 4,300 joules is the total change of energy in this system. So what we have here is a piston, a movable piston that can go up and down. And inside it we have gas. We're going to use this idea of a piston to illustrate some thermodynamic processes. So if we have what is called an isothermal, iso meaning same, thermal meaning temperature, what we're saying is the temperature in this situation does not change. So if we keep the temperature the same and we increase the pressure by pushing this piston down, what we're going to do is we're going to decrease, finish drawing my piston, we're going to decrease the volume. So as pressure goes up, the volume goes down, or as the volume goes up, the pressure goes down. So you can see here we have like a point on this curve. where we have this A prime, for example. Here we have a high pressure, and that is going to correspond to a low volume. So that's like pushing the piston down. High pressure, low volume. Or if we allow the piston to go up, that's going to increase the overall volume here. We have more volume. So here we have a high volume, and that corresponds to a low pressure. And these two curves here are showing us two different temperatures. So here we have the relationship between pressure and volume at a low temperature, and here we have the curve showing us the relationship between pressure and volume at a high temperature. So to have an isothermal process, okay, for a process to take place, a thermodynamic process, heat has to move from one thing to another. But usually, if you move heat from one thing to another, it increases its temperature. If we move heat, I don't know, if we put a spoon in a pot of boiling water, the heat from the boiling water will go into the spoon, and the spoon will get hot. So how is it that we can have an isothermal process where heat moves from one thing to another, but it doesn't change its temperature? Well, one example of that is geothermal heating. So let's look at this in the summer when you have air conditioning, a geothermal air conditioning system. We are taking heat from inside the house, and we are taking it and through a series of pipes dumping it into the earth. The earth is considered a heat reservoir. So because the earth is so large, the heat that we are taking from the house, putting into the earth, doesn't really change the temperature of the earth. We're not significantly increasing the temperature by moving that heat energy into it. So that's an example of an isothermal process where heat is flowing from one thing to another, and yet the temperature doesn't really change because we have this heat reservoir, this giant the Earth is like this giant reservoir that can accept a lot of heat without its temperature changing, mainly due to its incredible mass. Let's take a look at another term here. We're essentially just laying some groundwork here and some terminology, and we're going to put it all together a little bit later on. So if some of these things seem to not necessarily go together, we'll put it all together a little bit later. So an adiabatic process is where there is no heat flow into or out of a system. So an example here is the combustion in an engine cylinder. Now, in reality, when this occurs over and over and over again over a large period of time, of course the engine does get hot, and that's why we need radiators and cooling systems to keep the engine cool. So its running car engine is not truly adiabatic because there is heat flow out of that system. It's heating up the things surrounding it. But if we were to look at just one little spark, one combustion, if it happens theoretically very fast, so quickly that it doesn't really have time to escape out of the system, that approximates what we call this adiabatic process. So it's one in which a flow of heat occurs, but nothing escapes the system. It is entirely kept within that cylinder. There's no heat out, none of that. And there's also no heat in. There's none of that either. All of the heat energy is maintained within the system. It's nothing's getting in, nothing's getting out. Okay, let's look at a few more terms here. We're laying some groundwork. Isobaric. So baric, like barometer, has to do with pressure. And iso means same. So when we have an isobaric pressure, that means the pressure isn't changing. We have a process where we are going from here point A to point B. The volume is changing on this graph. Okay, our volume is getting bigger, but the pressure stays the same. Pressure doesn't go up or down. Here we have isovolumetric. Again, iso meaning same, and volumetric referring to volume. So with this type of process, if we go from a point A to a point B, the pressure drops, the pressure goes down, and yet the volume doesn't change, doesn't get greater or larger, it stays the same. So let's come back to this idea of a cylinder with a gas in it and a piston on top, and see how pressure and area and the distance that the piston moves up or down relates to work. So if we remember from back, I don't even remember what chapter that was. It was a long time ago. Might have even been chapter 2 or 3. We talked about how work is equal to a force times a distance. We talked about like pushing a box across the floor. We apply a force to it, we move it some distance, that is doing work. Okay, and if we think of force as being pressure times area, so we have this pressure acting on this piston, and if we multiply that pressure in newtons per meter squared times the area of the piston, which is in meters squared, that's going to cancel out and give us a force. So force is equal to pressure times area. So we can replace force with P times A. And if we then take a look at A times D, well, the area of the piston multiplied by the distance, I'm going to make this a bigger distance. Let's say this distance comes up to here. To illustrate this a little bit better, what we end up with, although my illustration is not very good, I'm trying to draw an ellipse there to represent the top of the cylinder, we end up with this cylinder that has a volume that is equal to area times D. So AD we can rewrite as volume, or the change in volume. So the work that is done by this gas inside this cylinder, if we were to raise this piston up, would be equal to the pressure times the change in volume. So by changing the volume, we're going to move the piston up and down, and that's going to do work, just like the cylinder in an engine. Now, if we have an isometric process, isovolumetric or isometric, that this is not going to change the pressure. I think that in fact this should be isovolumetric. An isovolumetric process, if the volume doesn't change, then that means the piston's not going up or down, so there's no change in volume. If there's no change in volume, if that is equal to 0, then 0 times the pressure is going to be 0, so no work is done. So to summarize here real quick, we've got our work is equal to P delta V, and for an isovolumetric process, no work is done.